My name is Hipparchus. I lived in the 2nd century before the birth of Christ, and I don't think I'd be bragging if I told you that I'm the father of the sciences of geography and astronomy. You know, I wrote more than 14 books, but unfortunately they have almost all been lost in the mists of time. I was responsible for the first catalogue of the stars, founded the field of mathematics called trigonometry, and even invented the astrolabe. Fortunately, my brilliant successor Ptolemy, 3 centuries after my time, inspired by my work, took up where I left off. And nowadays historians sometimes can't determine what was my contribution and what was his. Ptolemy's manuscript, the Almagest, was the first scientific treatise on astronomy, and his book Geography contains the first map of the known world. Geography and geometry both deal with the study of the Earth. Geography is concerned with making visual representations of the Earth, whilst geometry is concerned with measuring it. The shape of the Earth is roughly spherical. Let's forget for the moment that it's slightly flattened at the poles, and pretend that it really is a perfect sphere. You probably know too that all the points of the sphere are at the same distance from its centre. The arrow that you can see now, starting at the centre of the sphere and ending at a point moving on the surface, has a constant length. Let's choose an axis for our sphere, a line through the centre. When we cut the sphere along a plane that contains this axis, we carve out a great circle, which divides the sphere into 2 hemispheres. If we chop the sphere up using some sort of guillotine that slices down this axis, we trace out the meridians. These are half circles, going from the North Pole to the South Pole of the Earth. And now if we slice the sphere up along a plane at right angles to this axis, we get a bunch of circles called parallels. So now our sphere is covered by 2 networks of curves, the meridians and the parallels. One of these parallels should be very familiar. It's the equator, halfway between the 2 poles. For historical reasons, one of these meridians was chosen to be the principal meridian. It is the one passing through the Greenwich Observatory in England. To specify the position of some point on the surface of the Earth, we can start at the point where the Greenwich meridian meets the equator, and walk round the equator a distance, measured by an angle called the longitude, coloured red. Then you go up along a meridian some way, measured by an angle called the latitude, coloured green. finally arriving at our desired destination. Any point on the Earth is precisely described by just these two numbers, its latitude and its longitude. Since we need two numbers to specify a location on the surface of the Earth, we say that the sphere is two-dimensional, and mathematicians often call it S2. Finally, if we let our little plane leave the Earth and fly off into space, then to locate it we need to give three numbers: latitude, longitude, and the altitude above the Earth. Since we now need three numbers, to say where we are in outer space, we say that space is three-dimensional. Look at the paintings on the wall. There's a portrait of Ptolemy, the father of map-making. How do we draw the Earth? One method is to project it on a plane. Let's choose a city, Dakar for example. We draw a straight line from the North Pole through Dakar. Our line hits the table at some point that we call its projection onto the table. Any point on the Earth's surface can be projected onto the table in this way. The nearer our town is to the North Pole, the further away its projection on the table is. In fact, it can even end up off the table. For this reason, we say that the North Pole doesn't have a projection, or more correctly, that its projection is at infinity. The whole Earth, with the exception of the North Pole, can be represented on the plane of the table. This map of the world is called the stereographic projection. Of course, our stereographic projection doesn't preserve sizes. South America appears tiny compared to North America. To get a better idea of what this projection does, we'll roll the Earth along just like a giant ball, and we'll always project from the highest point. The projections of the continent waltz around in the plane, taking turns at becoming bigger and smaller. But if we take a closer look, we see that shapes don't change, even if lengths do. For this reason, we say that the stereographic projection is conformal. What happens to the meridians and the parallels under the projection? When we project from the North Pole, the meridians become radii emanating from the South Pole, and the parallels concentric circles. And as the Earth turns, you see that both the meridians and parallels always project to either circles or straight lines. The stereographic projection transforms circles drawn on the sphere into circles drawn in the plane, except for those circles passing through the pole from which we project, whose projections are in fact straight lines in the plane. Now here's our rolling Earth from below. From this point of view, we see the meridians and parallels form two bundles of circles. All of the meridians converge at 2 points, the North and the South Pole. Do you recognise this one here? Yes, it's the Greenwich Meridian, the end of the first stage of our journey towards the fourth dimension.
Now it's my turn to show you round the geometry garden. My name is Escher, and I was a Dutch artist in the 20th century. Geometry was a constant source of inspiration for me. I'm a past master in the art of drawing fantastic tilings. Look at this self-portrait in a spherical mirror. One of my most famous drawings shows lizards drawn on a plane that managed to break out of the paper. Now, perched on high, they contemplate their previous existence as flat life. To prepare ourselves for life in 4 dimensions, we are going to use the ideas behind both my engraving and a little book published at the end of the 19th century by Edwin Abbott, an English clergyman, called Flatland. Let's try and explain to these flat beings, these creatures living trapped forever in a plane, what our everyday life in 3 dimensions is like. Let's imagine that one of these lizards manages to escape his miserable existence for a moment and climbs out and up onto a viewpoint looking down on his world. How would he explain to his fellow reptiles the existence of objects in 3 dimensions? As a first attempt, he could try to pass some 3-dimensional objects through his flat world. Here, for example, is a tetrahedron with its 4 faces, passing through the lizard's plane. The flat creatures see a green triangle appear suddenly, then gradually shrink away. This is all they see, since their senses are entirely restricted and they cannot perceive anything outside of their plane. Each time that a lizard sees these green polygons appear, change shape and disappear again, he might imagine the form of the object that has just crossed his plane. To see how hard it is to visualize the form of a geometric body from its cross-sections, try to guess what is crossing through the plane now. A tetrahedron. And now, it was a cube. Of course, you have to remember that these lizards don't have the same perspective that we have. All they see is a sequence of polygons, and they'll have to develop an understanding of depth in order to fully appreciate the shape of the body. And now what? An octahedron with its 8 faces. And an icosahedron. It's a solid with 20 faces. And finally, the dodecahedron, 12 faces, 20 vertices and 30 edges. Now we're going to show you some cross-sections, and only cross-sections, and you have to guess the polyhedron hiding behind them. That was a tetrahedron. That was a cube. It's getting hard, isn't it? You see now that these creatures stuck in 2 dimensions have to develop good geometric intuition if they want to understand something of the 3rd dimension that we take for granted. We'll have just the same kind of problems to get a feeling for the fourth dimension. Here's a second method to explain polyhedra to our flat friends. Start by inflating a polyhedron so that the vertices and the edges are on the surface of a sphere. Then we stereographically project onto the plane of the lizards so that our two-dimensional friends may enjoy the spectacle. Of course, we can spin the sphere around and with it our tetrahedron just as we did before with the Earth. Let's take a look at the cube and see how many vertices, edges and faces it has. And now, here comes an octahedron. You see the 8 coloured faces. Look how the projections of the edges are arcs of circles. Now here comes an icosahedron. Its structure is more complicated, but it's not hard to understand even for the lizards. We can see 20 faces, 12 vertices and 30 edges. Can you count them all? Finally, here's a little geometric jewel, the dodecahedron. Now for some exercises. Let's take ourselves down into 2 dimensions and try to recognize the polyhedra from their stereographic projections. It's easy, isn't it? You can see the 4 faces, 6 edges and 4 vertices. There, it's a tetrahedron. Now, what's this one? 6 faces, each with 4 edges. That's right, it's a cube. That was harder, wasn't it? The faces are triangles. 5 edges start out of each vertex. There are a lot of faces, perhaps 20. It's an icosahedron. Well done. Let's look at the dodecahedron. Each face is a pentagon. If we count them, there are 12 faces. 3 edges start at each vertex. These 5 solids have always fascinated geometers. The Greek philosophers attributed a magical importance to them by associating to each of them one of the fundamental elements from which the world is formed. We call these figures the Platonic solids. So we agree then. It's not easy to get a feeling for the third dimension when you're flat. There is more than one way to do this, but our stereographic projection appears to give a good idea of what's going on. Now we'll have to get ourselves ready for the fourth dimension. We're going to have to use our imagination.
My name is Ludwig Schleffli. I am a Swiss geometer. I lived during the 19th century, and I'm going to open the door to the fourth dimension for you. Even if I say so myself, I was a visionary. I was one of the very first to understand that spaces with a high number of dimensions really exist, and that their geometry can be studied. If flat creatures living in a plane can understand three-dimensional polyhedra, then why shouldn't we understand polyhedra in dimension 4? One of my main achievements was to describe all regular polyhedra in dimension 4. What is the fourth dimension? A lot has been written on the subject. Science fiction writers never tire of talking about it. I'm going to explain things on the blackboard. You will see that this blackboard has a bit of magic about it. What's important is to prepare yourself to forget about the world which is familiar to us and to imagine a new world that our eyes and our senses have no direct access to. We'll have to be smart, just like the lizards were before. I'm going to climb on the top of a viewpoint that unfortunately you cannot see, and I'll try to describe what I see from there. But before we begin, I'll draw a straight line on the board. Let me just mark the origin here. Each point on this line can be located by its distance from the origin, with a minus sign if it is on the left, and a plus sign if it is on the right. Usually the number is denoted by x, and is called the abscissa. Since the position of a point on a line can be described by a single number, we say that the line has dimension 1. Now, I draw a second axis, perpendicular to the first one. Each point in the blackboard plane is now completely described by two numbers, usually denoted x and y, the abscissa and the ordinate. The plane has dimension 2. If you had to explain to some being living on a line what it is to be a point in the plane that is unknown to him, you could simply say, a point in the plane is just a pair of numbers. Let's go to the third dimension. The chalk now writes in the air and draws a third axis perpendicular to the two previous ones. A point in space is described by three numbers, x, y, and z. One could say to the reptiles that are curious to know about our world, a point in space is just three numbers. Let's go to the fourth dimension. One could try and draw a fourth axis, perpendicular to the others, but that's impossible. So we have to do something else instead. Of course, we might just say that a point in the fourth dimension is nothing other than four numbers, x, y, z, t. That doesn't help us a lot. In spite of the difficulties, we are going to try and get a feeling for this geometry. As a first attempt at understanding, we shall proceed by analogy. Here is a segment and an equilateral triangle. And finally, a regular tetrahedron. Our magical blackboard enables us to draw in space. How can we keep this up in 4 dimensions? Observe that the segment, the triangle and the tetrahedron have 2, 3 and 4 vertices respectively. Therefore, we can try to continue with 5 vertices. Let's go then. For the segment, the triangle or the tetrahedron, an edge connects each pair of vertices. So we have to connect the 5 vertices in pairs. We count 1 edge, 2, 3, 4, 5, 6, 7, 8, 9, and 10 edges. In the tetrahedron, there is a triangular face for each triple of vertices. We proceed in the same way, which gives us 2, 3, 10 faces. But if we keep going, by analogy, we have to add a tetrahedral face for each 4-tuple of vertices. There are 5 of them. That's it. We constructed our 4-dimensional object. We'll call this the simplex. Let's spin it around in space a little, as we did with the tetrahedron. Of course, you have to imagine the simplex spinning in a 4-dimensional space. What you see is only its projection on the blackboard. Touch complicated is that faces get tangled and they can cross each other. Well, some experience is required to be able to see in dimension 4. We're going to take the simplex, which is in 4-dimensional space, and move it gradually so that different cross-sections of it meet our 3-dimensional space. In the same way that reptiles could see a polygon appearing and disappearing, we will see a 3-dimensional polyhedron which appears, changes shape, and then vanishes. Here is the simplex passing through our 3-dimensional space. We're now going to meet more 4-dimensional polyhedra, passing through our own 3-dimensional world. Here is the hypercube, a member of the family that starts with the segment and continues up through the square and the cube. It has to be said that getting a feeling for the geometry from the slice method like this is rather tricky. I discovered the analogues of the icosahedron and the dodecahedron. They have complicated names, but I'll just call them 120 cell and 600 cell, since the former has 120 faces and the latter 600. Look at the 120 cell. It's just passing through our space. And now here's the 600 cell. Of course, when I say that a four-dimensional polyhedron has 600 faces, I mean three-dimensional faces. These 600 faces are 600 tetrahedra. As for the 120 cell, it consists of 120 dodecahedra. In a minute, we'll see how we can get to know them better. To observe these four-dimensional objects with our three-dimensional eyes, we can look at their shadows. The objects are still in 4 space, but they are projected on our 3 space, exactly like a painter might project a landscape onto his canvas. We've already done just this with the simplex. Here is the hypercube. Of course, it's spinning in space, so that we can appreciate all the details. Notice, for instance, that the hypercube has 16 vertices. Here's a little newcomer. It's the most beautiful of my discoveries. An object that I call the 24 cell. It has absolutely no analogue in dimension 3. It's a purely 4-dimensional creature. I'm very proud of my discovery. Look how wonderful it is. 24 vertices, 96 edges, 96 triangles, and 24 octahedra. A real little gem. Here is the shadow of the 120 cell, in all its majesty. A rather complicated majesty, you have to agree. Let's get inside and have a look at its structure. Look. "600 vertices, 1,200 edges. 4 edges start at each vertex. A completely regular structure. All vertices, all edges play the same role. It's a pity that the projection breaks the symmetry. Let's work your imagination a little. Imagine the object in 4 space, in which a huge group of rotations permutes all these vertices and edges. The champion is the 600 cell. like a gigantic macromolecule with its 720 edges and 120 vertices, and 12 edges starting from each vertex. Our exploration of four-dimensional polyhedra won't stop here, as their stereographic projections are bound to give us a better feeling for the geometry. The S2 sphere is in three-dimensional space and has dimension 2. In the same way, we can study the sphere in four-dimensional space. It contains all the points that are at the same distance from a center point. But now, to determine the position of a point on this sphere, we need three numbers. This means that the sphere has dimension 3, and of course we will call it S3. You will not be able to see this sphere in four-dimensional space because your space has only 3 dimensions and the screen only has 2. I can only call upon your imagination. To get a better understanding of four-dimensional polyhedra, we can do just what the lizards did with the three-dimensional polyhedra. We first inflate them so that they lie on a sphere, and then project this stereographically onto the plane. This time we'll inflate the polyhedron until its faces lie on a hypersphere in 4 space and project stereographically back into our own 3 space. I'm going up to the North Pole of the sphere in 4 space, and I'll project it down to you in your 3 space. You can't see where I am. Just remember how the lizards couldn't see their kinsman right up on his viewpoint either. Now we're in exactly the same situation. Here's the simplex. You can see its 5 vertices and its 10 edges. Of course, in this view, edges are circular arcs. So now we have a situation like that of the three-dimensional polyhedra, projected stereographically onto a plane. Here's the hypercube. It's easy to recognize it from its 32 edges and its 16 vertices. Seeing things this way is so much easier than with the shadow method or the three-dimensional cross-sections. Here's the 24 cell, with 24 vertices and 96 edges. Finally, the 120 cell and the 600 cell. Let's add the two-dimensional faces to get an even better view. The simplex, with its 10 triangular faces. Of course, these two-dimensional faces are pieces of spheres, just as before when we saw that the edges were circular arcs. The simplex is spinning in 4 space before being projected stereographically. Remember when the Earth was spinning like a ball and we saw the motion of the continents? Now and again, a face passes through the projection pole, and the projection becomes infinite. It looks like it blows up on the screen. Let's take a quick look at the hypercube. You see that the space is divided into 8 cube-shaped zones. These are the 3-dimensional faces of the hypercube. As for the 2-dimensional faces, they are squares, though rather bloated and twisted. There are 24 of them. Ah, my favourite, the 24 cell. Look at that. The 24 cell is really wonderful. 24 vertices, 96 edges, 96 triangles, and 24 octahedra. 8 edges start at each vertex. Here's the 120 cell. Let's try to understand its geometry better. 4 edges start at each vertex. The two-dimensional faces are pentagons. There are 720 of them. These 720 pentagons form 120 dodecahedra. Look at all those dodecahedra fitting nicely together. Isn't that amazing? Let's finish with the 600 cell, with its 600 three-dimensional tetrahedral faces, its 1,200 triangular faces, its 720 edges, and its 120 vertices. Trust me, there are 14,400 symmetries of 4 space which preserve this object. Well, there you are, we're done, with our first voyage into the 4th dimension. It's a dimension full of amazing things. Of course, the mathematician's imagination isn't limited to the 4th dimension. There are the 5th, the 6th, the nth dimensional, and even the infinite dimension. Each dimension has its own character, but it has to be said that the 4th is the prettiest. Why? Maybe because after all, it has a sort of physical reality. Einstein's relativity theory, dating from the early 20th century, postulates that space and time are somehow bound together into a 4-dimensional space-time. A point in this space-time is an event, characterized by its position in space x, y, z, and by the time t when it occurs. Dealing with relativistic physics therefore requires an understanding of 4-dimensional geometry. It is interesting to notice that the discovery of this 4-dimensional geometry precedes by some 50 years the discovery of relativity. It's one of the many interactions between mathematics and physics that the history of science delights in.
I'm Adrien Douady. My entire life's work in mathematics was centred on the complex numbers. My contributions helped to advance both algebraic geometry and the theory of dynamical systems. Complex numbers have a long history. You see here on the left Tartaglia and Cardano, mathematical pioneers who lived during the Renaissance. On the right, Cauchy and Gauss, who consolidated the theory during the 19th century. Complex numbers are not really as complicated as the name might lead one to believe. At first, they were called impossible numbers. Even today, they are still sometimes called imaginary. Well, it's true, it does take a little imagination. Yet today these numbers are everywhere in science and are not really mysterious anymore. In particular, thanks to them, one can construct beautiful fractal sets, something I worked on a lot. I even produced a film, The Dynamics of the Rabbit. It was one of the first animated films in mathematics. Let me begin by explaining the complex numbers on the blackboard. Mathematicians just love writing with chalk. You'll see in a minute that my ruler, this set square and protractor, behave rather oddly sometimes. Let's draw a graduated line on the blackboard. One of the most beautiful ideas in mathematics is to link geometry to algebra. This is the starting point of algebraic geometry. Just as we can add numbers, we can add points. Here is a red point on the line and another blue one. Let's add these 2 points. We get the green point. 1 plus 2 equals 3. When the red and blue points move, the green point, which is the sum, must move too. More interesting still is multiplication of points. Let's look at multiplication by -2, for instance. It transforms the point 1 into the point -2, of course. And if you multiply again by -2, you have to do the same thing. Change sides with respect to the origin and double the distance from the origin. You get 4, of course. If we multiply twice by -2, we have multiplied by 4. Multiplying by -1 is very easy. Each point is sent to the symmetrical point with respect to the origin. In other words, we do a half turn, a rotation by 180 degrees if you like. When we multiply a number by itself, the result is always positive. For instance, if we multiply by -1, we make half a turn, so that if we do it one more time, well, we come back to the initial point. This is why -1 times -1 is equal to +1. Simple enough. You see, for instance, that multiplication by -1 sends 2 to -2, and that if you multiply one more time by -1, you come back to 2. Obvious, isn't it? Therefore, there is no number which, multiplied by itself, yields -1. Another way of saying this is that -1 has no square root. But of course we are underestimating the inventiveness of mathematicians. At the beginning of the 19th century, Robert Argand had a really great idea. He said to himself, since multiplying by -1 is a 180-degree rotation, its square root is a rotation by 1/2 of 180 degrees, 90 degrees. If I do 2 quarter turns one after another, I end up doing a half turn. The square of a quarter turn is a half turn, hence -1. It's easy when you know how. Argand decided, therefore, that the square root of -1 is represented by the point which is the image of 1 by a 90-degree rotation. But of course this forces us to leave our horizontal straight line, since we have just agreed to associate a number to a point in the plane which is not on the line. As this construction is a bit strange, we say that this point, the square root of -1, is an imaginary number. And mathematicians denote it by I. But once we have the courage to leave the line, everything else is easy. We can represent 2i, 3i, and so on. Each point in the plane represents a complex number, and conversely, each complex number defines a point in the plane. Points in the plane become numbers in their own right. These numbers can be added, just like usual numbers. Look at the red point, which is the point 1 plus 2i. Let's add 3 plus I, which is the blue point. Well, you add them just as school children do. That gives us 4 plus 3i. Geometrically, this is just addition of vectors. You see that it's no problem to add complex numbers. Much more interestingly, these complex numbers can also be multiplied, just like real numbers. Let's see. We know how to multiply a complex number by 2, for instance. 2 times 1 plus 2i gives 2 plus 4i. Geometrically, multiplying by 2 is easy. It's just scaling up by a factor of 2. If we double the red point, we get the green point. Multiplying by I is not difficult either, since we know that I corresponds to a quarter turn. In order to multiply 3 plus I by I, we just have to rotate by a quarter turn. We get -1 plus 3i. Not so complicated, these complex numbers. And finally, we can multiply any two complex numbers with no problem whatsoever. For instance, let's try to multiply 2 plus 1.5i and 1 plus 2.4i. We proceed as usual. We first multiply by 2 and then by 1.5i, and we add the results. Therefore we get which is -2 plus 4.8i minus 1.5i plus 3.6i times I. But I squared is -1, since we invented I for this purpose. So we get -2 plus 4.8i minus 1.5i minus 3.6. And tidying up, that gives us -2 minus 3.6 plus 4.8i minus 2.5i, giving us in all -5.6 plus 3.3i. There you are. We know how to multiply complex numbers. In other words, we can multiply points in a plane. That's amazing. We thought that the plane was dimension 2, since 2 numbers are necessary to locate a point. And now I'm telling you that 1 number is enough. Of course, we changed our numbers, and now we are dealing with complex numbers. It seems the right time to define 2 notions, the modulus and the argument of a complex number. The modulus of a complex number z is just the distance from the origin to the point that represents z in the plane. Let's use the ruler to determine the modulus of the red point, which is 2 plus 1.5i. Let's see, it measures 2.5. The modulus of 2 plus 1.5i is therefore 2.5. For the blue point I get 2.6. And for the green point, which is the product of the 2 points, I have 6.5. As a rule, the modulus of a product of two complex numbers is just the product of the moduli of the two numbers. The argument of a complex number is measured by the angle between the abscissa axis and the straight line joining the origin to the point. Here, for instance, the argument of the red complex number is 36.8 degrees. The argument of the blue point is 112.6 degrees. And for the product, the green point, we get 149.4 degrees. That is the sum of the arguments of the two numbers. When we multiply two complex numbers, moduli are multiplied and arguments are added. Let's finish up our first encounter with complex numbers with the stereographic projection. Consider a sphere tangent to the board at the origin. Using stereographic projection, to each point on the board, that is, to each complex number, corresponds a point on the sphere. Only the north pole of the sphere, I mean the pole from which I'm projecting, has no complex number associated to it. We say that it corresponds to infinity. Therefore, mathematicians say that the sphere is a complex projective line. Why line? Because one needs only one number to describe its points. Why complex? Because this number is complex. Why projective? Because we added a point at infinity using the projection. Aren't mathematicians strange when they try to tell us that the sphere is a straight line? I'm going to show you some transformations. Transforming what? Well, if you don't mind, we're going to transform my portrait. Let's begin with something simple. The transformation z goes to z over 2. Each point on the photo corresponds to a complex number z that's divided by 2. We get another point. It's imaged by the transformation, hence a new picture. You see, no surprise, I just shrank to half the size, since each z has been divided by 2. This transformation is called a homothety. Let's go to the multiplication by I. Easy. We know that multiplying by I is just a quarter turn. Note that the modulus does not change, but the argument increases by 90 degrees. Indeed, this is quite a sophisticated way of saying that we just rotated the picture. Well, a bit more complicated. Multiplication by 1 plus I. Look at the complex number 1 plus I. It corresponds to the point with abscissa 1 and ordinate 1. Its argument is 45 degrees and its modulus is the square root of 2, using Pythagoras' theorem. Hence, a multiplication by 1 plus I amounts first to multiplying the modulus by the square root of 2, and then to adding 45 degrees to the argument. In simple words, one has to combine a homothety and a rotation. This is called a similarity. More interesting. We are going to transform the points z into their squares, z multiplied by z. Let's begin by placing the photo in a suitable place, flush against the coordinate axes. Then I zoom a little bit, since the squaring process will change the size of things, and I need space to show you this. Okay, now we can transform the photo progressively. Notice that the argument of z squared is twice the argument of z, so that the right angle on the lower left of the photo is doubled under the transformation. It has turned into a 180-degree angle. Let me place the photo somewhere else and let's look again at the same transformation z squared. You will notice again the same argument doubling. For instance, look at my index finger. Before the transformation, its argument is about 45 degrees. And after the transformation, it points upward at 90 degrees. But you can also observe that moduli are squared. Now let's go to a new transformation, sending the point z to minus 1 over z. Don't forget, with complex numbers one can add, multiply, but also divide. Not by 0, of course. Doesn't this image remind you of the Sistine Chapel? Large complex numbers with a large modulus become small when one takes their inverses, and conversely. Here is a similar transformation. Look at the formula. The value of k changes slowly. Some parts are expanded, others are contracted, but if one looks closely, the shape is preserved even though lengths are not. A circle remains circular even though it might grow. My hand grew, my face became smaller, but you can still recognize me. One more transformation, more involved. Well, this one is not really a weight loss program for me. But note once more that even though I got bigger, the shapes of small parts did not change. For instance, if you look at a button on my shirt, it keeps a circular shape. One says that these transformations are conformal or holomorphic. Rather complicated Latin and Greek words for saying that one preserves shapes. Indeed, with complex numbers, one can do quite a lot. One can even take the exponential, if you know what this means. But even if you don't know, look at the treatment I have to suffer from the exponential. Has my head disappeared? No. If you look through a microscope near the origin, you could see my beard. Now that you know about complex numbers, and you've seen some transformations, I will explain some of the objects I've been studying closely. Here you see a number of points. Some are blue inside the unit disk, and some are yellow outside. Let's perform the transformation z squared several times, and let's look at the result. You can see that the blue points stay inside the disk, and the yellow points, on the contrary, escape from the disk, and even escape from the screen. One says that the blue disk is the filled-in Julia set of the transformation z squared. Points outside the Julia set escape to infinity when one repeats the transformation indefinitely. But we can play the same game with other transformations, like for instance those of the form z squared plus c, where c is a complex number that we can choose at will. For each complex number c, we therefore have a Julia set whose shape changes when c changes. You can see a few examples here. Here is the one I called the rabbit. In order to understand how these shapes change, I will show you several things in parallel. On the left-hand side, the red side, you can see a point that will start to move. This is the point C. On the right-hand side, you see the corresponding Julia set. This is deforming as C slowly changes. But sometimes, for some values of C, the Julia set seems to disappear. One cannot see anything anymore on the screen. Like now, for instance. The truth is that the Julia set blew up into an infinite number of pieces so small that you don't see anything on the screen. Benoit Mandelbrot, who popularized fractal sets, suggested the study of this set, drawn in red, that describes the values of C, for which one can see the Julia set clearly on the screen. In other words, those for which the Julia set did not blow up into multiple pieces. Of course, this red set is called the Mandelbrot set, and I spent quite a lot of time studying it. To finish, I suggest that we look closely, very closely, at this Mandelbrot set, and zoom inside so that you can appreciate how beautiful it is. Let's go. Here it is. Admire. For once, I will not explain everything. Imagine the Mandelbrot set as a black island, surrounded by a tropical sea, and that you can see the bottom of it. Really, you are looking at truly microscopic details. If the Mandelbrot set were the size of a soccer field, well, we would be looking at details the size of a single atom, of the order of a millionth of a millimeter. Maybe you're wondering why I got interested in this. First of all, because it is beautiful, and because understanding these objects gave me much pleasure. For me, this is reason enough to spend time on these questions. But also because in these transformations that look so simple, one can find the essence of chaos, such a fundamental concept in modern science. Simple things generating rich structure. To study complicated phenomena through their simplest incarnation, this is often the role of the mathematician.
Circles in space that are arranged so as to create beautiful ornaments. In order to understand better the three-dimensional sphere in four-dimensional space, I will show you how to fill the space with circles, and thus create what mathematicians call a fibration. By the way, my name is Heinz Hopf, and I am one of the main contributors to the development of topology during the first half of the 20th century. Look at this toric surface, filled with circles that appear to be linked. Let me explain this picture to you. Circles, spheres and tori are among the simplest objects studied by topologists. A topologist tries to understand the connections between these objects. I worked in Berlin, Princeton and Zurich, and one still comes across my name often in contemporary mathematics. Poincaré-Hopf theorem, Hopf invariant, Hopf algebra, Hopf fibration. Let me paint my portrait for you. I published the discovery of my fibration in 1931. But as always, I have to say that I relied upon many predecessors, like Clifford for instance, who you see here, and who worked in England during the 19th century. Let's begin with some explanations on a blackboard. Well, a whiteboard this time. What do you see? A two-dimensional plane? Well, yes and no. This is indeed a two-dimensional plane, but it is a plane of complex dimension 2, or in other words, a space with real dimension 4. Go on, make an effort. Each point in this plane is determined by two coordinates, but each of these two coordinates is a complex number, which, remember, is itself defined by two real numbers. Each of the axes is a complex line, so that each point on these axes has one coordinate, which is a complex number. For instance, here you see the point 2 minus I on the first axis. The same is true for the other axis, the y-axis. Here we can see the point 1 minus 2i on this axis. Now our whiteboard is magical, but not enough to be able to show us the two planes simultaneously. If we try to depict them in three-dimensional space, they will intersect along a line, but in four-dimensional space, they intersect only at the origin. After all, they are axes. Now what do you see? A circle? Yes and no. What you see, or rather what you should imagine, is the set of points in four-dimensional space that are at distance 1 from the origin. In other words, this is nothing other than the three-sphere S3. Well, of course you need to have a little imagination. Let's try to see at least how this sphere intersects the first axis. The three-sphere intersects the first axis in a set of points on this axis which are at distance 1 from the origin. You see, the three-sphere intersects the first axis in a circle. The same is true for the second axis, which intersects the three-sphere in a circle as well, the blue circle. Now what is true for the horizontal line and the vertical line is equally true for all lines going through the origin. Here you can see the line with equation z2 equal to minus 2z1. But we could do the same with any line z2 equal to a times z1 for any complex number a. In this manner, the three-sphere in four-dimensional space is filled with circles, one for each complex line going through the origin in our plane of complex dimension 2. Careful though, in the picture you get the impression that the red circles intersect each other, but this is not the case in the reality of dimension 4. Lines only meet at the origin, so their intersections with the unit sphere don't intersect at all in fact. I was the one who discovered this decomposition of the sphere into circles, and ever since it is known as the Hopf fibration. Why fibration? Well, you should think of the fibres of fabric. We are going to look at all that using stereographic projection. Imagine that we project the three-sphere from the North Pole onto the tangent space at the South Pole, which is our three-dimensional space. Here is the projection of one of the circles which, as we have seen, is the intersection of one complex line and the three-sphere. But there are many such circles, one for each complex line going through the origin. For each complex number a, we can consider the line z2 equal to a times z1 and its associated circle. Let us vary this number a, or, what will amount to the same thing, let us rotate this line in order to see how the circle changes. Notice that sometimes the circle appears to be a straight line, but this is simply because it passes through the North Pole of our three-sphere. Let's look at two of these circles simultaneously. In the lower left-hand corner, they are the two moving complex points, one red, the other green. You can see the circles associated to the red and green points. Notice that these two circles are linked together like two links of a chain. It is impossible to separate them without breaking them. For the fun of it, let's consider three circles. Look at the dance of these three linked circles. Now let's take many more complex lines, chosen randomly, and let's look at them all at once. The circles fill up the space, and no two of them intersect. This is an example of a fibration. Let's try to understand this better by returning to the board for a moment. Look, we have a hop circle for each line. Each one of these lines has an equation of the form z2 equal to a times z1, where a is a complex number, the slope of the line, and is indicated by the red point moving on the green line. Actually, the vertical axis does not have such an equation, but in this case, we may say that a is infinite. Don't forget that a is a complex number. The green line is also a complex line. So it is a real plane, of course. Summing up, the complex lines that we are interested in are completely described by a point on the green line and an additional point at infinity. But we already saw that if one adds a point at infinity to the complex line, we get the usual two-sphere. Once more, this is stereographic projection. So the complex lines that interest us are described by points on the yellow sphere, the two-dimensional sphere S2. So we have a circle for each point on the two-sphere. But a circle is a sphere of dimension 1, isn't it? All these circles fill up the 3-sphere. Each point on the 3-sphere belongs to a single circle, and therefore defines a point on the 2-sphere. In this way, we get a projection from the 3-sphere to the 2-sphere. Complicated, isn't it? Mathematicians say that above any point of the base S2, there is a fibre which is a circle S1, and that the total space of this fibration is the sphere S3. I am very proud of my fibration, all the more so because it has become a fundamental object in topology. Let's come back to the two-dimensional sphere and its parallels. Above each point of the two-dimensional sphere, we should imagine a Hopf circle. Look at what is above one of the parallels of S2, the equator for instance. Here is what is above another parallel, which is moving southwards. Why does the torus seem to get thinner? Because above the South Pole, there is of course only one circle. And above the North Pole, one sees a straight line, actually a circle, going through infinity. This is the red line. Well, let us spin all this around now. Rotations, yes, but rotations in four-dimensional space, of course. To be honest, I have to say that some of these pictures were already known long before me. The existence of 4 families of circles on the torus is usually attributed to the Marquis de Villarceau, but one finds earlier clues in a sculpture in Strasbourg Cathedral, for instance. Take a torus of revolution. That is, the surface described by a circle rotating around an axis in its plane. Look at the section of the torus by a plane. Notice how I choose the plane. One says that it is bitangent to the torus, simply because it is tangent at 2 points. Now look carefully. The plane cuts the torus along two perfect circles. This is Villasow's theorem. A plane which is bitangent to the torus cuts it along two circles. Of course, there is not just one bitangent plane. Here is another one, cutting the torus along two other Villasov circles. And one can do the same for all other bitangent planes. We just need to rotate around the axis of symmetry. You see, through each point on the torus of revolution, one can draw 4 circles, obtained by suitable slices. One of these circles is a parallel. Another is a meridian. Then a first Villasov circle, and a second one. And since one can do this at any point of the torus, we see that the torus is covered by 4 families of circles. 2 circles of the same family do not intersect. A blue circle intersects a red circle in a single point. A yellow circle and a white circle intersect in 2 points. These are Villasov circles. Take a good look at the yellow circles. These are Hopf circles. Remember when we looked at what is above a parallel in the fibration? We saw a torus covered with linked circles, just like this torus covered with yellow circles. And what about the white circles? Well, they are fibers of another Hopf vibration, the mirror image of the first one. To finish our stroll, we will take a torus of revolution with its 4 families of circles. Imagine it in a 3-dimensional sphere. Rotate the torus inside the 3-dimensional sphere and finally project it stereographically onto 3-dimensional space. In this way, we obtain surfaces that are also covered by 4 families of circles, the so-called Dupin cycloids. Sometimes, when the torus passes through the projection pole, the surface becomes infinite. In this movement, the two faces can even be switched. The inner face of the torus is pink and the outer one is green. A simple rotation in the fourth dimension and, bingo, green turns into pink and pink into green. Isn't that magnificent?
Doing mathematics means, above all, proving what one claims. We have seen that the stereographic projection sends circles on the sphere, not going through the pole, to circles in the plane. And now we are going to prove it. Even though this has been known for many centuries, it is I, Bernhard Riemann, who will present this proof to you. I am frequently honoured, since one speaks today of the Riemann sphere. Proving is much more than showing. It is not enough to see in a movie that some curve looks like a circle, to be sure that it is indeed a circle. A mathematical proof must use reasoning to be convincing, and has to explain why it is indeed a circle. The great Euclid, during the 3rd century before Christ, formulated the rules of the mathematical game in his book, The Elements. A proof has to rely on facts, that themselves have to be proved. But one has to start with something, so that some statements have to be accepted without proof. These are the axioms. Therefore, mathematics appears as a gigantic construction whose foundations consist of the axioms, and such that each brick rests on the previous one. In order to prove the theorem about the stereographic projection of circles, we should, in principle, start with the axioms. Of course, we have no time for that now. We will assume that we already know the theorems of geometry which are studied, say, in secondary school, and we will prove this theorem. Start with something simple: the intersection of a sphere and a plane. We see that if a plane cuts a sphere, and if it is not tangent to the sphere, then the intersection is a circle. We can see it, but why is it true? How do we prove it? Well, let's consider an arbitrary plane, coloured in blue. We can draw the perpendicular from the centre C of the sphere to the plane. Let's call P the foot of this perpendicular. Consider 2 points A and B on the intersection of the sphere and the plane. And let's look at the two triangles CPA and CPB. They share a common side, CP. Both have a right angle, since the angle at P is of course a right angle, since the plane is perpendicular to CP. But note that the hypotenuses AC and BC have the same length because A and B are on the sphere and are hence at the same distance from the centre C. But remember Pythagoras' theorem. Since our two right-angled triangles have two sides of the same length, their three sides must have the same length. Hence, we have proved that PA and PB have the same length. That is, that A and B are on the same circle with centre P, in the blue plane. Therefore, we have proved that all points which are both on the sphere and the plane belong to some circle. Does that imply that all points on this circle are on the sphere and on the plane? A priori, no. We still have to prove it. Let A be a point which is on the sphere and the plane. Consider the circle in the blue plane with centre P and that goes through A. We will prove that this circle is contained in the sphere. Let B be some point on this circle. Look at the two triangles CPA and CPB. They share a side, CP. Both are right-angled triangles since the angle at P is a right angle. But the lengths of PA and PB are equal, since A and B are on the same circle with centre P. Again, using Pythagoras' theorem, we conclude that the hypotenuses have the same lengths. CA equals CB. This means that the point B also lies on the sphere, since it is at the same distance from C as A. That's it. We have proved that when a plane cuts a sphere, the cross-section is a circle. Now let's look at a diameter APB of our circle. And let's place it in the plane of the screen. The blue planes appear as a straight line on the screen, and the sphere appears as a circle. Let's draw the tangents to the circle at A and B. They intersect in a point S. Of course, the line CS is again a symmetry axis for our figure. Why? Well, because the triangles CAS and CBS are equal. Why? Because they are both right-angled triangles having a common hypotenuse, and the sides CA and CB have the same length. Why? Well, because these are two radii, of course. You see, if we had to go right to the end of all the arguments, this movie would be the longest in the history of the cinema. Look, we have just proved that any circle drawn on a sphere can always be thought of as the contact locus between a cone of revolution and a tangent sphere. If you like, the sphere is like ice cream in a cone. Well, we mustn't forget what our aim is: to show that the stereographic projection carries circles onto circles. Let's first prove what mathematicians call a lemma. Here is the tangent plane to the sphere at some point A, seen from the side. Now here is the tangent plane at some other point B, also seen from the side. These two planes intersect on a line D, but at present we only see one point, since this line is perpendicular to the screen. The figure that you are looking at is symmetric with respect to the bisecting line of the two lines that we see. This three-dimensional picture is symmetric with respect to the bisecting plane of the two tangent planes. Choose some plane containing the segment AB. It intersects the line D in a point M, unless it is parallel to D, of course. The symmetry of the figure with respect to the bisecting plane shows that AM and BM have the same length. The triangle ABM is isosceles. Here it is. That was our lemma. Well, now we can prove our theorem using what we have just learnt. Consider a circle on the sphere which does not go through the North Pole. We want to show that its projection is a circle. Look, if instead of projecting onto the tangent plane to the South Pole, we projected onto some other parallel plane, the famous theorem of Thales would imply that all the projections are similar. Hence, in order to prove our theorem, we may choose the projection plane as we wish. Of course, as long as it is parallel to the tangent plane to the South Pole. Well, let's place our yellow circle in a cone. Remember? The ball of ice cream in a cone with vertex S. Well, we're going to project onto the horizontal plane through S. The point B projects onto a point D. But look at the figure. The triangles AMB and DSB are similar. Why? Well, again, Thales' theorem. Do you agree? Now, remember our lemma. The triangle ABM is isosceles. Hence the same is true for the triangle BDS, so that BS has the same length as DS. When B moves along the yellow circle, the segment BS keeps tangent to the sphere. Its length is therefore constant. Since BS and DS have the same length, the moving segment DS also retains a constant length. Let's see, saying that DS has a constant length means precisely that D describes a circle with centre S, so that the projection of our yellow circle on the horizontal plane through S is contained in a circle. We have seen that by Thales' theorem this implies that the projection onto the tangent plane to the South Pole is also contained in a circle. QED, quod erat demonstrandum.